Hello, welcome to the WEC Sim training course. My name is Kelly Rule, and today I'm going to give you an overview of the WEC Sim open source software. The overview will provide an introduction to what the WEC Sim software does, how it can be used, its requirements, the underlying theory, and how to access additional resources. WEC Sim is the wave energy converter simulator. It's an open source software that's used to simulate wave energy converter dynamics and operational and extreme waves. It's a time domain rigid body equation of motion solver based on the Cummins formulation. The WEC Sim software is developed in MATLAB Simulink and is publicly available on the WEC Sim GitHub repository using the link provided. The WEC Sim software is funded by the Department of Energy, the Water Power Technologies Office at the Department of Energy, and it's a joint venture by Sandia and NREL. Our first release of the WEC Sim software was in June 2014, and our latest release was released in September 2022. The Wave Energy Converter Simulator, also known as WEC Sim, simulates wave energy converter performance and dynamics in operational and extreme waves. It's a time domain rigid body equation of motion solver based on the Cummins formulation. The open source software is developed using MATLAB Simulink and is publicly available on GitHub using the link provided on the WEC Sim repository. The project is funded by the U.S. Department of Energy, Water Power Technologies Office, and it's been jointly developed by Sandia National Laboratories and the National Renewable Energy Laboratory. The first WEC Sim release was in June 2014, and our latest release was in September of 2022. The WEC Sim open source software is licensed under Apache 2.0. For more information about the Apache 2.0 license, please access the link provided. An open source license allows users to use and modify the WEC Sim open source software to meet their needs. So why use WEC Sim? WEC Sim has the ability to model the dynamics and performance of devices that are comprised of rigid and flexible bodies, power takeoff systems, mooring systems, joints, constraints, cable blocks, and more. The image below shows the overview of the WEC Sim workflow, where you start with a 3D geometry and device specifications. You incorporate the relevant numerical methods, meaning multi-body dynamics, rigid body constraints, hydrodynamics, PTO, and mooring, and you can use WEC Sim to get information about the performance, dynamic response, and loads of your wave energy converter design. When modeling a device, it's important to consider where the tool that you're using falls in terms of computational time and fidelity. A tool like WEC Sim is a time domain solver that's based on linear potential flow and incorporates nonlinearities. Thus, it's a mid-fidelity solver. It's higher fidelity than linear frequency domain models that are just direct boundary element method solvers, but not as high fidelity as LES or CFD. As mentioned previously, WEC Sim has the ability to model the dynamics of devices that are comprised of rigid and flexible bodies, power takeoff systems, mooring systems, cables, and more. WEC Sim relies on hydrodynamic coefficients that are derived from frequency domain boundary element method simulations that are used to model the relevant hydrodynamics. As you can see in the left-hand side of this figure, outside of the WEC Sim core functionality, we rely on boundary element method solvers such as Willamette, Aqua, Nemo, or Capitaine to provide hydrodynamic coefficients that are then parsed into WEC-Sim using our boundary element method input-output solver, BEMIO. This then parses the data into an H5 data structure that's read by the WEC-Sim input file. Encompassed by the dotted line box, you can see that WEC-Sim.m, also known as our WEC-Sim executable, is what is used to run the WEC-Sim model. All external inputs are defined in the WEC-Sim input file and executed by WEC-Sim.m. WEC-Sim models each body separately and solves the time domain equations of motion for each body in 6 degrees of freedom. The 6 degrees of freedom modeled by WEC-Sim for each body are defined on the right-hand side of this figure, where the incident wave direction is in positive x, heave is positive z, and sway is positive y. Rotation about x is roll, rotation about y is pitch, and rotation about z-axis is yaw. WEC-Sim's underlying theory implements the Cummins impulse response function formulation, thus allowing us to solve the time domain equations of motion for a wave energy converter. By moving to the time domain, we can incorporate nonlinearities into the WEC-Sim model. From left to right, we incorporate an F equals ma formulation where our mass times acceleration is equal to a summation of our hydrostatic restoring force, our wave excitation and diffraction, which is from coefficients from boundary element method solutions, our radiation force, which incorporates added mass and radiation damping, also from our boundary element method solutions, a viscous force, which can incorporate nonlinearities, and PTO and mooring forces, which are also externally defined and can incorporate nonlinearities. Both the radiation and diffraction method are used to calculate the hydrodynamic forces from frequency domain boundary element method solvers based on the Cummins impulse response formulation. On the left-hand side, you see the formulation for the radiation force incorporating infinite added mass in a convolution between the radiation impulse response function and velocity. In terms of the excitation force, it is calculated by a non-causal impulse response function that convolves the excitation impulse response function with the wave surface elevation. WEC-Sim has a few software requirements or dependencies. First, users need to define their 3D geometry and mesh the geometry. Commonly used tools to define this computer-aided design or CAD geometry are Rhino, SolidWorks, and ANSYS. Next, users will need a boundary element method solver to solve for the hydrodynamic coefficients. We support Wilmette, Capitaine, Nemo, and Aqua boundary element method solvers. Lastly, since WEC-Sim is built on a MATLAB Simulink framework, we require MATLAB Simulink Simscape Multibody. We also provide a boundary element method input-output parser called BEMIO. The general steps to simulate a floating device using WEC-Sim include the following. 1. Generate a CAD geometry and mesh the device. 2. Calculate the hydrodynamic coefficients using a boundary element method solver such as Wilmette, Nemo, or Capitaine. 3rd, run BEMIO to generate an H5 file. 4a, write a WEC-Sim input file. 4b, build the Simulink model. 5, run the case. And 6, analyze the WEC-Sim output using a post-processing script. WEC-Sim is publicly available via a GitHub repository using the link provided. On the GitHub landing page, you'll see a series of repositories that are relevant to WEC-Sim. WEC-Sim is the WEC-Sim source code repository. WEC-Sim applications includes additional cases of applying advanced features for WEC Sim. We additionally provide other resources that are relevant to users, such as a WEComp control competition model, legacy versions of Vimeo, and others. Additionally, WEC Sim has extensive online documentation. The online documentation can be used to support both the main version of the repository, the main branch, and also the development branch using a drop-down box on the bottom left-hand corner of the documentation page. The documentation can be accessed using the link provided, and we provide information such as an overview of the WEC Sim software, an introduction to how to use and apply WEC Sim, a theory manual, a user manual, and a developer manual for users who want to make modifications to the WEC Sim source code themselves. The WEC Sim team also provides user support via an online forum using the link provided. The online forum is managed through the GitHub issues page where users can submit questions using a template, either a theory or implementation, a developer issue, an application case, or a bug fix, among others, to interact with the WEC Sim development team. We do our best to respond to issues in a timely fashion and look forward to hearing from you. Thank you very much for joining the overview section of the WEC Sim training course. We have a host of other information available on our WEC Sim website, including other sections of this online training course. And as always, if you have any questions for the WEC Sim development team, please post an issue on our issue board. Thank you very much.